Hello everybody, welcome to our YouTube video. Today we are going to demonstrate our Signals and Systems third semester project. So we will start with discussing about analog filters. Alright, let's take a step back and talk about the basics of analog filters. Analog filters are circuits that are specifically designed to process continuous signals in the analog domain, unlike digital filters which operate on discrete data. There are a few common types of analog filters, each with its unique purpose: low pass, high pass, band pass and band stop filters. Now let's break them down into parts. Low pass filters allow frequencies below a certain cutoff frequency to pass through while blocking higher frequencies. High pass filters do the exact opposite, letting high frequencies through and blocking the lower ones. Band pass filters allow only a specific range of frequencies to pass while blocking frequencies outside that range. And finally, band stop filters, also known as notch filters, reject a particular frequency range while allowing frequencies outside that range to pass. So why choose analog filters? Well, they are often simpler to implement for real-time signal processing, especially for applications requiring continuous signals. Analog filters don't need to convert signals between analog and digital, which saves processing time and preserves the natural qualities of the signal. Analog filters are widely used in audio equipment, communication systems, and instrumentation. So now we are going to talk about the 4 popular filters that are to be used for the experiment. First is the Butterworth filter, then is the Chebyshev filter, Elliptic filter and the Bessel filter. Now let's take a look at the Butterworth filter. Known for its maximally flat frequency response in the passband, the Butterworth filter is unique because it doesn't have any ripples in the passband. As you can see here, the Butterworth filter's response curve is very smooth, making it ideal when you need a filter with no passband ripples that won't distort your signal. However, the smoothness comes at a trade-off, and the Butterworth filter has a slower roll-off around the cutoff frequency. You will often find the Butterworth filter's applications like audio processing, control systems and instrumentation. Next up, let's look at the Chebyshev filter. Named after the mathematician Pafnuty Chebyshev, this filter has 2 main versions: Chebyshev type 1, Chebyshev type 2. Chebyshev filters are known for their ripple in either the passband or the stopband depending on the type. Type 1 has ripples in the passband and a maximally flat stopband, while Type 2 is the opposite with a flat passband and ripples in the stopband. The key advantage of using the Chebyshev filter is its sharper roll-off compared to the Butterworth filter of the same order, making it efficient in filtering unwanted frequencies. However, this also comes at a cost of introducing ripples, so it is best used in the applications like audio processing and instrumentation.
Now, let's dive into the elliptic filter, also known as the Carver filter. This is one of the most efficient filters in terms of transition sharpness. The elliptic filter is designed to have both ripple in the passband and the stopband, but it offers the sharpest transition between passband and stopband compared to other filters. So it's an excellent choice when you need a high level of frequency discrimination in a very narrow range. Although the elliptic filter sacrifices some smoothness in both the passband and stopband due to the ripples, it makes up for this with a steep cutoff slope. This is incredibly useful in applications like signal analyzers and radio receivers, where spreading close frequencies is crucial.
Now, let's talk about another important filter type, the Bessel filter. If you are working on applications where signal timing and waveform shape are crucial, the Bessel filter could be a go-to solution. The Bessel filter is known for its linear phase response in the passband. This linearity means it can handle signals with minimal phase distortion, keeping the shape of waveforms intact even as it filters out unwanted frequencies. This quality makes it ideal for applications like audio processing, radar, and data communications where preserving the original signal shape is crucial. Unlike a Butterworth filter, which focuses on smooth amplitude response, the Bessel filter's strength lies in its phase fidelity. It maintains a consistent time delay across frequencies, ensuring signals stay synchronized. To summarize, the Bessel filter is perfect when you need to retain the waveform's integrity and avoid phase distortion. However, it sacrifices some roll-off steepness, so while it won't filter out frequencies as sharply as other filters, it excels in keeping signals clear and undistorted.
After analyzing these filters using MATLAB, we have decided to use the Butterworth filter for conducting the experiment. Now my friend Aryan will talk about the code in detail.
Now we will use MATLAB to understand demonstration of Butterworth, Chebyshev, Elliptic and Bessel filters through their frequency responses and also by applying a test signal. First, we have defined a sampling frequency at 1 kHz and a time vector by taking inverse of sampling frequency. A signal is generated by addition of sine waves operating at 25 Hz and 50 Hz respectively. Noise is generated by using random function by keeping a 0.5 scaling factor and further added with signal in order to make a noisy signal. Filter specifications like cutoff frequency is kept at 100 Hz and order of filters at 5. As of now, we were defining parameters such as time vector, sine waves, and noisy signal in time domain. But to play with amplitude and frequency, we have to convert the noisy signal into frequency domain. These lines nothing but perform transfer function where B is assigned with zeros and A with poles. Now talking about programming the filters, defining order, Nyquist ratio, also called as the normalized frequency, which is twice of cutoff frequency upon sampling frequency, and mentioning the filter type is common. Difference occurs in the frequency response. First, Butterworth filter, which has no ripples in passband as well as the stopband, due to which nothing will be mentioned about the ripple amplitude while using Butterworth function. Talking about Chebyshev filter, which has ripples in passband, its ripple amplitude will be mentioned while using the function. Elliptic has ripples in both passband as well as the stopband, so accordingly two ripple amplitudes will be mentioned. As MATLAB provides Butterworth, Chebyshev and elliptic filter functions with respect to digital filters, but Bessel is provided in terms of analog filters, due to which while using Bessel function, order and angular frequencies are mentioned instead of mentioning the Nyquist ratio. Further, analog to digital conversion is done using bilinear functions separately. Once B and A coefficients are calculated, they are filtered with respect to noisy signal. Further, we have used frequency Z function in order to plot frequency responses of all filters having 512 number of evaluation points for smoother graph. Next, we have plotted all filtered signals with respect to time in order for comparison. If we look at the comparison of filtered signals, the Butterworth and Bessel has somewhat achieved the original signal compared to Chebyshev and elliptic filters. Still, Butterworth is preferred most because its attenuation rate is neither too fast like elliptic nor too slow like Bessel. Now we will quickly understand same program by applying an audio input. Audio read function calls the audio file, performs analog to digital conversion, and stores audio data and its sampling frequency. Some audio players are defined to show the output, and filtered audio is saved. Remaining all code stands the same.
So have to provide space for a transistor. You cannot have crooked lines. Okay, so since the space is you're not saving, so have to provide space for a transistor. You cannot have crooked lines. Okay, so have to provide space for a transistor. You cannot have crooked lines. Okay, so since the space is you're not saving space by not fabricating a MOS transistor.
Easily notice that though audio signal was filtered, but the vocal amplitudes were suppressed. This occurs because if in a noisy signal, if noise and audio waves both operate at same frequency and at same time, then vocals will be suppressed with noise. From this, we can understand that order of filters should neither be too low, resulting into negligible filtration, and nor too high, resulting into vocal suppression.